Jean-François.
So sorry if you have to see me again, but it's because I'm presenting on behalf of my collaborator in Surrogate. He couldn't make it here, so Antonio, which is who is a postdoc, working with Picea for me in research work and with me at the same time, and François Pimon, which is who is a researcher in Avignon, in France, working with terrestrial as well. So I will talk quite briefly actually about an algorithm, LBOX, to estimate the plant area density from TLS point clouds acquired in forest environment. So introduction, pretty obvious, but plant area density refers to the total plant surface compared to the area density, but it is one of the most important parameters, of course, it characterizes the exchange process between atmosphere and surface. We all know that TLS give us a lot of information about the 2D structure, but raw TLS is from a different point of view and everything is unequally sampled in the forest, extremely noisy. And an interpretation of PED, plant area density from raw TLS data is normally incorrect. I mean, you need to apply some correction on your data to be able to get good estimate. Recent studies use fossilization approach to estimate PAD, but we lacked in the past estimation tools for estimating PAD at plot level. In this context, the study aims to estimate the PAD of virtual and of real forest plots from the LSM by fossilization approach. The implementation actually of the PAD estimator for forest plot is the LBOX, and it is a plugin in Computation. Computation is an open source platform for processing TLS data, focused on forest inventory, but it's more for developing the algorithm and testing the algorithm. It's more like a laboratory rather than really operational platform. We test the estimated, or assess the estimated PAD with a virtual forest. So again, my 3D model that I talked about earlier, some of them have been used for that. Evaluate the impact of parameters such as the voxel size, but we are pretty sure we heard in the past presentation voxel size. I won't steal the punch, but pretty know the answer already, and assess the influence of conclusion. To meet this objective, we test the developed algorithm using the following dataset. So 4 virtual plots simulated by an architect, again, from Eastern Canada, so it was in Newfoundland, the Eastern provinces with the balsamea fir spruce. So, and we have also 6 actual plots, 400 square meter, of which 3 coniferous from the province of Newfoundland, the Eastern, and 3 deciduous plots from New Brunswick, which is another province, but a little bit on the west. It's in the east of Canada, but it's neighbor of Newfoundland. So to reduce occlusion, we have multi-scans with the different configuration. In case of the virtual plots, we use ray tracing, actually physically based ray tracer, PPRT, to generate point clouds from 5 different point of view within the virtual plots. And it was also the same kind of configuration for actual deciduous plots. For the coniferous plots in Newfoundland, but on another dataset that we use for the Polish studies, actually they use 9 scans to be able to see everything, and the plots are still 400 square meters. So it was pretty messy, so they didn't want to miss anything. 9 plots and 9 scans for that to be sure. The method is we start by voxelization of the TLS point clouds, and then the computation of PAD for each individual point cloud for each view. We use several PAD estimators that are implemented, including the Beer Lamberts and the maximum likelihood estimator with bias correction. And then we merge the PAD from individual scans with a weighted sum of the individual PAD. And in our case, the DTM was not really a critical issue because our side would be flat, but now we apply normalization with the DTM for that and compute the vertical profile of estimated PAD. PED computation, we developed an estimator based on real numbers at voxel level. From the, in this estimator from the number of emitted pulses and the number of returned pulses. So we have the 1 minus RDI, which is the relative density index, is the ratio between the number of returns within the voxel and the number of beams that reach the voxel end. And actually it's a bit more complex, but it tells the story. And then you inverse the Poisson law to get the DAD using the Fourier projection function, the loss function, and the dV, which is the voxel dimension. If I remember correctly, G was pretty much assumed spherical for coniferous and the other, I can't remember. There is also bias correction for the finite size of element and unequal path of poles traveled in the voxel. So validation with the virtual forest, it was even, of course, it's an ideal case. There's no understories model actually within the architect in our case, but there's still noise because at the top of the crown, so there's still a huge amount of occlusion within 3 crowns. So, but the algorithm performed quite well. I mean, our score of 98 is pretty good. Accuracy of the PAI, integrated the integration of PAI, accuracy of 97%. Of course, the multi-scans improve the accuracy of the estimated PAD. You can see if we take only the central scan versus the multi-scan approach, and similar results were observed for the real plots. So in this case, we have the coniferous and deciduous. Multi-scans improve 30 to 40% of the PAD estimated by one scan. You can see the difference on this curve here. We observe also really high occlusion on the on the eye part of the top of the canopy on deciduous plots because it was acquired in the Newfoundland conditions. So there's this difference between coniferous and deciduous plots. Actually, you can see more occlusion at the top. The influence of voxel size, I mean, is a bit not a big surprise. The optimal voxel size was 10 centimeters in the virtual plots. Those were Balsamea and Laxfruit. 10 centimeters, relatively the size of the shoot, that, like Martin told us, is the foliage unit that drive this kind of voxel size. Yes, you can have, you can guess when you set up your tires. Smaller voxel size resulted in overestimation of wood surface, and bigger voxel size resulted in underestimation of foliage surface. You can see the different here for the virtual plots. For the real one, due to the large leaf, deciduous result were less sensitive to voxel size. Even though if it's less sensitive, I would still consider to use the leaf size as a voxel size anyway. It's a good rule of thumb actually. And small voxel had an overestimation of wood surface. That was not for the virtual plots. So just you can see the curve here. In conclusion perspective, we presented the method where the plots implemented with the Abies software, which is a plugin in computation right now. With simulated forest, we showed an accuracy of more than 90% in the vertical profile of the PAI and the integrated PAI. The result depended on the resolution of the voxel grid, again 10 cm for coniferous, mostly yes. The occlusion occurred highly in one scan, but could be considerably reduced by multi-scan. There's nothing new there, usually and our main perspective would be the estimation of the LAD by an integration of the leaf-wood preparation by the Lidar method. We have seen some here this conversion Lidar. And also now, I just saw the result just before. I mean, here in Brazil, they tested the approach with the virtual plot with the PSN for the deciduous, and they observed actually just less accuracy at the top of the canopy because of the percentage of occlusion because of the leaf there. So that fit the same result that we observed in Canada. So that's pretty much it. If you have, I will try to answer the question, but some details I will miss it, so you can contact Banto, so we will answer.